So we're going to continue on with our lecture on organic chemistry. And now the next topic that we want to look at as we continue to talk about hydrocarbons we were talking about alkanes last time, and now we'll move on to talk about some other families of compounds. So remember, with alkanes, we had the formula CnH2n plus 2, and alkanes are molecules that only contain single bonds. So now what we're going to move on to is to talk about alkenes. And alkenes are going to have the formula CnH2n, and these are going to be hydrocarbons that contain one double bond. So that's the rationale for going from CnH2n plus 2 to CnH2n. So that ANE ending is talking about only single bonds. The ENE ending is indicating that there's a double bond. So let's use the example of ethane to make sense of the change in the general formula. So with ethane, we know that's 2 carbons, all single bonds, so each carbon has 3 hydrogens attached. And then we can compare that to ethene. So now the ANE ending for just a regular alkane with no double bonds, and the ENE ending to indicate the presence of a double bond. And the formula tells us CnH2n. So when I connect my 2 carbons, there'll be a double bond between them, and then each carbon will get 2 hydrogens. So we're still thinking about the valence, right? And the valence of 4 is satisfied in these cases because we have a double bond between them, so they each have 4 electrons around them. So then let's talk about ethane. When we look at this carbon, we'll call it sp3 hybridized, and that's to indicate that there are 4 electron pairs around that atom, and it's using 4 orbitals, sp3, in order to do this. And we would say that its electron domain geometry and molecular geometry are both tetrahedral. On the other side, with ethene, with 3 electron domains, remember a double bond still counts as 1 domain because the second connection is a pi bond through p orbitals instead. This is sp2 hybridized, and then kind of like I've drawn it here, it's trigonal planar for both the electron domain and molecular geometries that we're looking at here. So that's why we say CnH2n instead of CnH2n plus 2, because you can imagine you're effectively taking 1 hydrogen away from 2 adjacent carbons, and then they're sharing an electron pair between them. So when I talk about naming alkenes, there's a little more detail here. First, we're going to need to indicate the location of the double bond and also talk about the overall chain length. So for example, if I name my molecule 2-hexene, well, it's telling me first, based on the hex, that it's a 6-carbon chain. Based on the ENE ending, it's telling me that there's a double bond, and the 2 is telling me the location of the double bond. So we can still draw this exactly like we would alkane chain in line angle notation. So I can just draw 6 carbons in a row, 2, 3, 4, 5, 6. but now it's telling me between carbon 2 and carbon 3, I need a double bond. So whatever number precedes the hexene tells me the lower numbered carbon that's going to be participating in the double bond. So 2 hexene is telling me that it's between carbon 2 and carbon 3. Well, what if I said that I had 3 hexene instead? So 3 hexene, again, the hex is telling me that it's a 6 carbon chain. ENE is telling me that there's a double bond. And then the last piece of information is where it's located. 3 hexene means it's between carbons 3 and 4. So now here we go. 2, 3, 4, 5, 6. And so now, if I number my carbons, 1, 2, 3, 4, 5, 6, 3 hexene means this double bond is between carbon 3 and carbon 4. So that's a distinction between those two structures. Let's do one more example of naming alkenes, and then we'll move on to molecules with triple bonds. So 2-octene, you can kind of follow the same pattern as before. We know that oct means 8 carbons, ene means there's a double bond, and now 2 is telling me the location of the double bond. So now we can draw 8 in a row. So 2, 3, 4, 5, 6, 7, 8. If I number these, 1, 2, 3, 4, 5, 6, 7, 8. The double bond is between carbon 2 and carbon 3. So that would be 2-octene. Okay, so that was with one double bond. Now we'll talk about molecules with one triple bond. So these are called alkynes. So now I've got the YNE ending to indicate a triple bond. So triple bond. And as a result, now you can imagine between two adjacent carbons, I have to remove 2 hydrogens each. So these guys are going to have the formula CnH2n minus 2. So 2 fewer hydrogens than we'd expect from the alkene. So we can do kind of the same thing, right? We can draw ethane, ethene. So here's ethane. And we can draw ethene with a double bond between the two. And now we can draw ethyne with a triple bond between the two. So now removing another hydrogen each, and then this becomes our structure. So last time we were labeling our carbons. For ethane, it would be sp3 tetrahedral. For ethene, sp2 trigonal planar. And so that makes the carbon in ethyne sp and linear. So this gives us a bond angle of 180 degrees. So that's why I've drawn the carbon, all 4 of the atoms, in fact, collinear with each other to indicate that 180 degree angle. Remember, the trigonal planar is 120. Tetrahedral, we don't really show it in our drawing, but that one is 109.5. Okay, so that's a good example to start with for your alkyne with ethyne. I'll draw a couple more of them as well. So the naming of alkynes pretty much works the same way. We'll use the parent name to indicate the total number of carbons, YNE ending to indicate the presence of a triple bond, and then a number to talk about where it's going to be located. So for example, if I had 2 pentyne, then the pent tells me it's a 5 carbon chain. YNE tells me there's a triple bond, and the 2 tells me the triple bond is located at carbon 2. So because the carbons attached to the triple bonded carbons need to be collinear, it'll look a little bit odd when we draw this, but it'll be like this. So triple bonds throw people off as they're looking at them, so let me number. It's 1, 2, 3, 4, 5. So 4 and 5, I'm going back to showing the zigzag line of a typical line angle, but carbons 1, 2, 3, and 4 need to be collinear with each other because this angle has to be 180 degrees. So sometimes it gets a little odd to draw a triple bond, but that's the way that you want to do it. Let me draw one more of these. I'll do 3 hexyne. 3 hexyne. So same sort of plan, right? Hex tells me it's a 6 carbon chain. Yne tells me there's a triple bond. And the 3 tells me the location of the triple bond. So you can also draw this by putting the triple bond in place first and then figuring out what to do. So we know that those are carbon 3 and 4. And then the carbons coming off of each of these need to be collinear. So now I've drawn carbons 2 and 5. And then just to continue the zigzag, I can draw 1 and 6 like that, and that would be a reasonable way to draw 3 hexyne. Okay, so hopefully that's making sense for seeing all the patterns for alkane, alkene, alkyne. We're going to add one more to this group, and then we'll move on to molecules that have more than just carbon and hydrogen. So the last one in this group are what are called the cycloalkanes. And the cycloalkanes, the cyclo means that there is a ring structure in them. So just like alkenes, they're going to have the formula CnH2n, but now the rationale is slightly different. Right, in an alkene, we imagined taking away hydrogens from 2 adjacent carbons so they could make a pi bond. In the case of the cycloalkane, what we could imagine is removing 1 hydrogen each from the 2 end carbons and then connecting them together. So for example, right, if I had hexane 2, 3, 4, 5, 6, the 2 groups on the end are CH3s, right? Technically, there are 3 hydrogens on each of these carbons. And so imagine zipping the ends together. So what I could imagine happens is that if I remove 1 hydrogen each from the 2 ends, then each of those carbons would be available to grab onto something else, and we could attach them to each other. So this is definitely not a reaction we're capable of doing. I can't zip together the ends of a simple hexane, but just to visualize what's going on, this will kind of show you how we make cyclohexane. So when I draw it, it's pretty much just going to look like a hexagon. And so now what I've effectively got are 6 CH2 groups all attached to each other in a loop, right? If I imagine this carbon, it's already attached to 2 carbons, so it has 2 hydrogens on it. And each one of these, in order to reach its valence, is going to have 2 hydrogens attached. So that gives us the formula C6H12. So there's no longer a 2n plus 2 because the two, all I've got are a group of CH2 groups that are all attached to each other. So if I think about what some of these other ones would look like, I could have a 4-membered ring. That would be called cyclobutane. I could have a 5-membered ring. That would be called cyclopentane, and that just looks like a regular pentagon, more or less like that, and etc. I think I could have also shown you in the beginning a 3-membered ring, cyclopropane, which is just going to be a triangle like that. So those are all the different typical hydrocarbons that we see. That pretty much shows you most of what we're thinking about in the simple structures that just contain carbon and hydrogen. So after this, what we're going to start to look at are more complicated molecules. So we'll start to involve oxygen and nitrogen as we start to think about all of that. So let me wrap this one up here just on this topic, and then we'll have one more short